Think about it for a second. From the AC in your car that makes a summer day just bearable, to the fridge in your kitchen keeping your food safe, cooling is a huge part of modern life. But here's the thing. The technology we all rely on has a massive and growing environmental problem. And that problem, well, it creates an incredible opportunity for a whole new solution. It's a wild thought, right? It sounds like a total paradox, but it's the reality we're living in. The ways we make things cold are, in fact, major contributors to global warming. The real question is, just how big of a contributor are we talking about? It's huge, just absolutely massive. Globally, refrigeration and air conditioning are responsible for a staggering 17% of all energy consumption. Let that sink in. Nearly 1/5 of all the power the world generates is just for making things cold. And honestly, the energy use is only part of the problem. The real culprit is the technology inside almost every single cooling device today. It's called vapor compression. It works by using chemical refrigerants called hydrofluorocarbons, or HFCs. And these things are just nasty greenhouse gases. Some are literally thousands of times more potent than carbon dioxide. With emissions growing like crazy, around 8 to 9% a year, we've hit a breaking point. Global agreements are now forcing a phase out. So the race is on to find a fundamentally new and better way to keep cool. And that brings us to a seriously elegant solution, the electrocaloric effect. What if, instead of compressing and expanding gases, we could cool things down just by using solid materials and a simple pulse of electricity? No harmful chemicals, no noisy high-pressure compressors, just a solid and an electric field. Okay, so what is this effect? At its heart, it's a really special property that only some materials have. When you hit them with an electric field, they heat up. And when you take that field away, they cool down. It's a direct, almost magical conversion of electrical energy into a temperature change, all happening inside a solid material. To get this, we gotta zoom way in, all the way down to the molecular level. So normally, the material has these tiny electric dipoles that are all jumbled up and pointing in random directions. It's a state of high chaos, or what scientists call high entropy. Think of it like a messy room. Now, when we apply an electric field, it's like a drill sergeant shouting, "Attention!" All those little dipoles snap into a perfectly ordered, aligned structure. We've cleaned the room. This sudden drop in chaos, or entropy, actually releases energy in the form of heat. The material gets warm. But then, here comes the magic. We switch the field off. The dipoles instantly rush back to their preferred, messy, chaotic state. And to fuel that transition back to chaos, they need energy. So they suck in heat from their immediate surroundings, making the material itself get cold. The takeaway is really simple. Apply a field, it gets hot. Remove the field, it gets cold. Okay, so a single pulse of hot and cold is a neat party trick. But how do you turn that into a continuous cooling machine, something like an air conditioner that can run all day? Well, let's look at how you build a real system out of this effect. You do it with something called an active electrocaloric regenerative cycle, or AER for short. Now, this diagram might look a little complex at first glance, but it's really just showing 4 simple stages that create a continuous heat pump. The key parts are that special solid material, you see it as the gray block, and a fluid, like planold air, that we shuttle back and forth. Let's just walk right through it. First, we zap the material with the electric field, and just like we said, it heats up. Then, we blow some air across it, from the cold end to the hot end. That air picks up the heat and carries it away. Step 3, we turn off the electric field, and bam, the material suddenly gets cold. Finally, we just reverse the airflow. Air now flows over the super chilled material, gets cold itself, and then goes on to cool whatever space we need. You just repeat this cycle over and over and over, and what you have is an active pump, moving heat from one side and dumping it on the other. So now that we know how it works, the billion-dollar question is it any good? How does this brand new tech stack up against other ways of creating cold? Well, its closest cousin in the solid-state world is a technology called magnetocalorics, which, as you can probably guess, uses a magnetic field instead of an electric one. But the difference is huge from a practical standpoint. To get a strong magnetic field, you need powerful, heavy, and really expensive rare earth magnets. But generating a strong electric field, that's way simpler and cheaper. This means electrocaloric devices have the potential to be much smaller, lighter, and more cost-effective. And the performance gap? It's not even close. When you model the absolute best electrocaloric materials against the best magnetocaloric ones, the results are just stunning. As you can see on this chart,
Electrocaloric systems could achieve more than double the temperature difference and a mind-blowing 600% more cooling power. That's not an incremental improvement, that's a potential leap forward.
And when you compare it to the old school tech in your home right now, vapor compression, the advantages are crystal clear. You swap out those high GWP gases for a simple, stable solid. You get rid of noisy, vibrating compressors and replace them with silent, solid-state electronics. And on top of all that, you have the potential for even higher efficiency, all with a zero global warming footprint.
Okay, this all sounds fantastic in theory, right? It sounds great in computer simulations, but is it real? Has anyone actually built one of these things and made it work? Let's take a look.
This is not science fiction. What you're looking at is an actual, physical test rig built at the United Technologies Research Center. This piece of hardware was designed for one purpose: to prove that the principles we just talked about can work in a real device to cool air, right here in the real world.
So how far along are we? Well, on what's called the Technology Readiness Level Scale, or TRL, this tech is sitting at about a 2 or a 3. What that means in plain English is that the basic science is proven, and its fundamental ability to work has been demonstrated in a lab. It's that crucial step right after the I have an idea phase, but before you start engineering a commercial product.
And what did that lab prototype actually do? It achieved a direct air cooling temperature drop of 8.4 degrees Celsius. That's about 15 degrees Fahrenheit. I mean, that is a significant, tangible cooling effect from a first-generation module. It's the proof that the core concept absolutely works as planned. An 8.4-degree drop is a fantastic proof of concept. So, what does the future hold? What is the ultimate potential we're talking about here? Just listen to this quote from the UTRC report to the Department of Energy. A quadrillion BTUs. That is a number so big it's almost hard to comprehend. We're talking about enough energy to power millions and millions of homes for an entire year. The potential here isn't just to make a better air conditioner. It's to totally disrupt the entire heating and cooling industry. Now, of course, there's still a long road to travel before this is in your house. The challenges are pretty much what you'd expect. Scientists and engineers need to figure out how to manufacture these advanced materials at a massive scale, make sure they can last for decades of constant cycling, and really optimize the whole system. The next big milestone is to get this technology out of the lab and into real-world field trials.
So this leaves us with a really fascinating final thought. For the last 100 years, our world has been cooled by compressing gases. But it's entirely possible that the next century of cooling will be silent, have no moving parts, and be based on the elegant physics of a solid crystal. It is a fundamental shift in how we think about staying cool, and the journey to get there has already started.